All right, so here we have problem 12 from the section 4.5. We're going to be dealing with some of these variations of parameters. And so the biggest thing that we need to do here is find a particular solution. But because the forcing function on the right-hand side is so strange, it'd be difficult to guess it. And so hence, we're going to use variation of parameters. If I could just look at it through inspection and figure out what it is, that would be quicker. If I had more typical function on the right-hand side, just the e to the t or just some sort of polynomial, I could do undetermined coefficients, but here we're going to do variations. So the first thing we're going to do every time is find our homogeneous solutions. So when I do that, I imagine there's a 0 on the right-hand side, and I do my work, and I'll find out that, well, if I wanted a general solution to the homogeneous case, it'd be some constant times e to the t plus some constant times e to the negative t. That would be my general solution for the homogeneous case. Sometimes, you'll see people write this simply as I have a homogeneous solution of e to the t and another homogeneous solution of e to the negative t. Either one of those is fine ways of writing it. I prefer to write it in the general solution. That way, when I'm doing my particular guess with our method, we can just switch out the c's for v's. Or now these v's are in fact functions of t. And what we'll find is if we were to plug this back in and demand one other little condition, the whole thing would reduce then with this guess to a little system of equations. So the system says that if I have e to the t v1 prime plus e to the negative t v2 prime, I'm going to demand that that's 0. Notice we switched the v1s to the right-hand side just because it looks a little bit more like what you do when you solve systems of equations. Nothing else. Then we take a derivative of these sort of homogeneous parts, and we get e to the t v1 prime minus e to the negative t v2 prime is equal to our forcing function, e to the t divided by t. So now we have to solve this system. We could do either the methods that we know, we could do it algebraically. We could use Cramer's rule if we wanted. There's a formula that just gives you Cramer's rule directly. So for this one, what I might do is notice because these ones line up so nicely, I might do it algebraically and just add straight down. So if I add straight down, I'd have 2 of these. 0 is equal to e to the t divided by t. So then I could solve this algebraically for v1 and find that v1, I'll do this in green, or v1 prime, I should say. That will simply be equal to 1 divided by 2t. Now, if I need to find a v2, I'll just plug it back in. So to find v2, I'll just say, well, we can do either the top one or the bottom one. Let's do the top one. So e to the t, plugging this in, divided by 2t plus e to the negative t, v2 prime, that's equal to 0. So solve this algebraically, and I'll end up with v2 prime is equal to negative. So we'd subtract this off and then divide by e to the negative t. So this would give you 2t on the bottom and e to the 2t up in the numerator. So here is my v1 prime, my v2 prime. My voice cracked there for a minute. Good. So notice what we've done. We started out with a problem. Start out with a problem here where we solve a homogeneous equation. We change out those constants for functions, and then turns into this, reduces to this system of equations. This jump is a bit of a jump, but it's really good to have that memorized so that you don't have to plug it in every time, plug in this particular solution, because it gets pretty messy. Now then we solve this system of equations either through Cramer's rule. I did it here algebraically. And so we're almost there. Notice our particular solution, we just need v1 and v2. but we have v1 prime and v2 prime. So to finish this off, we need to integrate these. So let's go over to the right here and integrate these two little functions. So for this first one, to get v1, it would be the integral of 1 over 2t dt. And so this right here, a lot of people might like to bring out the 1/2. Say, oh, I know that one. That's 1/2 natural log of t. Okay, so there's your v1. For v2, this one might be a little bit more annoying. v2 is going to be the integral. I'm going to also bring out the negative 1/2 out in front here. So e to the 2t divided by t dt. So to solve this one, you may look for different substitutions or whatnot, but try as you like for this one. Let me show you. I plugged it into Wolfram Alpha here. The integral of this is a very gnarly function, and it's not typically analytic using our more standard functions, and so I don't want to do that. So what I'm going to do is, in fact, just leave the integral in there. So if I were to do this undetermined integral, that would be a fine way of doing it. But what is also a little bit more typical is when I want to leave it inside of the integrand here, I might change up my variables a little bit and just say, this could be integral from 0 to t, or whatever you want, from t sub 0 if you choose, and just switch out to a dummy variable. Either one is fine. Now, that's all I'm going to have. I have to stick with that. So let's plug this all in here. So we say that our y particular, then, if you recall, I don't think you have to recall. I can show you over here where it was. Y particular is v1 times e to the t plus v2 e to the negative t. So y particular now is 1/2 natural log of t times e to the t plus, or we can, since it's negative, plus negative, so a half this hunk of junk, 2s over s, yes, times e to the negative t. Now I'm going to put that in front as well. And there's your particular solution. If you want to get the whole general solution, you would add this to what we had before. So the whole most general solution would be y is equal to constant e to the t plus some other constant e to the negative t, then plus, this stuff, all this stuff right there. There you go.